Hello, everyone. This is the second lecture, and we're still talking about linear systems. In lecture 1, we defined what a linear system is, and we learned how to convert a linear system into an augmented matrix, as well as the so-called elementary operations, the 3 elementary operations, which we can use in case we need to do any change for the matrix without affecting the solution. In this lecture, we will learn how to solve or how to use these elementary operations in order to convert the system into an easier one and then solve it. But before that, we still need to define something called the raw echelon form of a matrix and the reduced raw echelon form of a matrix. So we need to define what is meant by the raw echelon form of a matrix, or REF, and then we will learn what is meant by the reduced raw echelon form of a matrix, because we're going to use these in order to solve this system in an easier way. Let us start with the raw echelon form first of all. We say that a matrix is expressed in the raw echelon form if and only if the following 2 conditions are satisfied. So let's say you have a matrix, any matrix, right? Condition number 1, if there is an entire zero raw, like something like this, everything is 0. If there exists 1 or more zero raws, they must be at the bottom of the matrix. So for example, you might have 3, 2, and -1, let's say, 4, 5, and 2, and let's say 0, 0, 0. I'm saying if there exists 1 or more zero raws. If there exists such raws, they must be at the bottom. Okay? If there is no zero raw, then we do not bother with the first condition. I'm saying if there exists a zero raw. That's the first condition. Second condition is the following. Before I talk about the second condition, let's put this in mind. In every raw, in every single raw, the first non-zero entry is called the leading entry. So let's say in the first row, as you can see, 3 is our leading entry. Let's assume here that this was a 0. Okay, so what is the leading entry in this case? It's 5. Okay, some of them call it the pivot element, or the element in the pivot position. But let's stick to the leading entry. All right. The second condition, we go back to the raw echelon form, or REF. The second condition is that as we move to the bottom, as we go to the bottom, I mean from the first raw to the second raw to the third raw, etc., the leading entries should move from left to right. Left to right. So, in other words, in this matrix, as you can see, or as we said, this guy here is the first leading entry. What about the second? This is our leading entry. Let's say the third leading entry was here. So, as I am moving down, it's shifting to the right. That's good. But here, it has shifted to the left. Right? So this is not an REF. Or in other words, let's remove this first. So let's say you have this here is 0. And let's assume that this is 6, for example. Now, yes, this is this works. Why? Because as you go down, the leading entry is moving to the right. Or you can think of it as the stairs. You see? So as you go down, the stairs are, if you want, if you look at the screen, the stairs are moving like this to the right. So whenever you have such form, this is in the REF. So 2 conditions. The first condition, again, is that any zero raw, if it exists, has to be at the bottom. Second, the leading entries should look like this. As I move down, right, the leading entry, the corresponding leading entry has to move from left to right. Let's do some examples. This is example 1. So is this matrix in the REF or not? Let's start. Condition number 1, any zero raw, if it exists, has to be at the bottom. And yes, it is at the bottom. We do have a zero raw, which is at the very bottom. That's good. Second, we should have this ladder or these stairs thing, right? So what are the leading entries? If you like, you can circle the leading entries in every single raw, and then it becomes easier, right, to keep track of these leading entries. So as you go down and moving from left to right here, there is no leading entry. So here we go. That is in the REF. That's example number 1. Let's do more. What about this example? Condition number 1, any zero raw, there is no zero raw, right? So we just ignore it. Condition number 2, let us circle the leading entries. The leading entry in the first raw is this guy, 3, and the leading entry in the second guy is 4. And yes, we are going from left to right as we are moving down. So yes, this is also in the REF. What about this matrix? No zero raws, good. Condition 2, we have to circle the leading entries first of all. So that's our first leading entry, and this is our second leading entry. As I move down, look, this is moving from right to left. We don't have these stairs, right? So these stairs pointing to the right, I mean. So this is not in the REF. Okay. It is not in the REF, good. But can I make it look like REF? Can I convert it into the REF or into an REF? The answer is yes. How? Again, using elementary raw operations. What do I do here? Well, I can simply what? I can simply interchange these two raws, right? So it becomes what? This becomes, so R1, I will interchange it with R2. As we said last time, whenever you put this double arrow, this means I'm swapping two raws. And this becomes 2, 5, and 3, and 0, 1, and -3. And yes, this is in the REF. One more thing I want to mention about the REF. Now, let's say for some reason, this is in the REF, as we said. Let's say I want to multiply this raw by any number 3. So this becomes what? 3 times 0, 0, 3 times 1, 3, and 3 times -3, that's a -9. Is it still in the REF? Yes, it is in the REF, right? I can multiply it by any number. So what am I trying to say here? What I'm trying to say is that any matrix can be converted into an REF, good, and the REF, or the reduced echelon form of any matrix, is not unique. You can have many REFs for the same matrix, as we saw here, right? In the first case, before multiplying it by 3, this raw, it was in the REF. I multiplied this raw by 3 or any other number, it's still REF. It's still in the REF. It's still respecting the two conditions that we mentioned. So yeah. So in short, the REF of a matrix is not unique. Now let us move on to the RREF, or the reduced raw echelon form. In order to say that a matrix is in the RREF, it has to satisfy the following conditions. Condition number 1, it has to be in the REF. So it must be expressed in the REF. If it's not in the REF, we don't bother, we do not continue. It's definitely not in the RREF. Well, from the name, it sounds like reduced raw echelon form. So it has to be in the first place raw echelon form. It's not surprising, right? Good. Moreover, there are 2 more conditions. Every leading entry, or all the leading entries, are or must be 1s. So if a leading entry is not 1, it's not RREF. Okay? If the leading entry, let's say, is 10, I have to divide the entire raw by 10, for example, in order to convert it into RREF. So this is additional to the REF. That's the second condition. Third condition, every column which contains a leading entry, let's do it like that, which is actually, as we said here, 1, must only contain this leading entry as the non-zero element. In other words, all the columns which contain leading entries must have all the other entries as zeros. So it has to be the only non-zero entry in the column. So each column, I'm talking only about the columns which contain leading entries. So in this column, the leading entry, which is 1, which is the leading one, must only be or must be the only non-zero entry in this column. Okay? So REF, all the leading entries are 1, and all the columns which contain these leading entries has all other entries as zeros, except for the leading entry. Of course, let's do examples in order to make it more clear. Let us check this matrix. So first of all, it has to be in the REF. Is it in the REF? Yes. No zero rows, so we ignore condition 1. And we have these stairs, right? Let's circle the leading entries. That's the first leading entry. That's the second leading entry in the second draw, and that's the leading entry in the third draw. So as you go down, yes, we are moving from left to right. So it is in the REF. Then we move on to the RREF. So what are the additional conditions? All the leading entries must be 1s, and yes, they are 1s. Beautiful. Now, I look at the columns. I'm talking about the last condition here. I will look at the columns which only contain the leading entries. I'm talking about this column, and this column, right? In each column, as we said, the leading entry must be the only non-zero element. So this is good. Yes, it is the only non-zero entry in the entire column, as well as the second column, as well as the third column. Do I look at this column, the fourth column? No, we don't bother. Why? Because this column does not contain any leading entry, so I ignore it. So we only look at the columns which contain leading entries. And this is a common mistake. Some students get confused here. So they say, well, we have more than non-zero entry in this column. Of course, it doesn't matter, right? Because here we don't have any leading entry. We don't have any leading entry, so we don't bother with that. So we only look at the columns which contain leading entries. Let us do one more example to make sure that everything is good, and we move on to something else. What about this matrix? Is it in the REF? Obviously, yes, it is in the REF, right? What about the leading entries? Let's circle them. This is the first leading entry. This is the second leading entry. All of them are 1s. Good. What about the columns which contain the leading entries? I'm talking about the first column and the second column only. We don't look at the others, right? So the leading entry in each of these columns is the only non-zero entry in the entire column. So this is also in the RREF. Okay, now we know what an REF and what the RREF are of a matrix are. Now we are able to go back to the linear system, and I'm going to show you how to use these techniques in order to convert any linear system into an easier one and solve this system easier or in an easier way. And here I'm talking about the Gaussian elimination method and the Gauss-Jordan elimination method. All right. Before I start with this system, I just want to say one more thing about the RREF. We said that the REF is not unique, right? A matrix might have more than one REF. However, for the RREF, any matrix, or there exists an RREF for every single matrix, but it is unique. So that's the difference between the REF and the RREF. The RREF is unique, not like the REF. Cool. Let's say we have such a system, and I want to solve it using the techniques that I explained before. Well, you might see that this is an easy system. We can do it manually. Yes. But again, as I mentioned in the previous lecture, we might have larger systems. I'm talking about thousands or tens of thousands of variables. So in this situation, we really do appreciate these methods, which are the methods I'm going to talk about in a minute. So the idea is the following. The first method is that if in some way, we are able to cancel or to get rid of these two variables in the last equation, in the final equation. Again, if in some way, I will show you what is meant by that, I was able to get rid of these guys, all the variables except one, in the very last raw, then I will be able to find Z, right? Cool. Then, in the raw just up, the raw just before, if I was able, again, in some way, to get rid of X, so I'm only left with Y and Z. But I have found Z before, right? So if I plug in Z here, I will be able to find Y. Then I move up again. I have Y and Z. I plug them in, I get X. Okay? So that's the idea. Even if you have a larger system, we start at the very bottom, right? We cancel everything except one variable. I find it. Then in the row above, I cancel all the variables except two, the one that I found before and the one that I'm going to find now. And then like this, keep going like this backward, okay? And eventually I'll be able to solve all the system. So this way of plugging backwards is called a back substitution method or back substitution. And that's exactly what the Gaussian elimination method is. So the Gaussian elimination method is to do back substitution. And how do I convert it like that? How would I be able to get rid of X and Y and then X, etc., without changing the system? I will convert it into the RREF. So, as I will show you now, I'm going to write the system in the augmented form. I want to convert it into an augmented matrix and show you all the steps in details. You might be saying that, well, if I convert it into an augmented matrix and converted the corresponding coefficient matrix into the REF, then I will be doing Gauss elimination. What if now we converted the coefficient matrix in the augmented matrix? What if I converted it into the RREF? That's a natural question because actually we explained REF and the RREF. Well, if we convert it into the RREF, then we will be solving this system in the so-called Gauss-Jordan elimination method. So we'll be using the Gauss-Jordan elimination method. And that is what I'm going to show you. I'm going to show you how to solve the system in the Gauss-Jordan elimination method. If you understand the Gauss-Jordan elimination method, then you will have understood the Gaussian elimination method as I will show you in the explanation. So our first step is to convert this linear system into an augmented matrix and start applying elementary raw operations. All right, this is our augmented matrix. I'm going to show you the recipe, if you will, or the algorithm that I usually use, and it works for any system. I first of all convert the very first entry. I'm talking about the leading entry in the first try, convert it into 1. Then I convert everything underneath. I'm talking about this entire column. I convert everything underneath into zeros. So 1, then everything and all the remaining entries in the column to zeros. Then I move on to the second row, and I convert this into 1 and do the same for all the other elements. So all the other elements in this column will be zeros. Then I move on to the third row. I convert this into 1 and convert the rest into zeros. So 1, then everything zeros. Then another 1 in the second row, everything zeros, and so on. Okay, let's see. In order to convert this into 1, I have to multiply the entire first row by half. So R1 becomes what? Becomes half R1. So our new matrix becomes what? Becomes 1, 1 and 2. Of course, I have to do it for all the elements. So 16 divided by 2 is 8. What about the other entries? What about the other rows? I do nothing. I just copy them. Copy everything. -1, -2, 3, 1, 3, -7, 4, and 10. Good. Now I have to convert all the entries here, which are these, -1 and 3, I have to convert them into zeros. Oh, how would I do that? In order to convert this and this into 0, this means I have to apply changes to the second row and the third row, and I can do that simultaneously at the same time. This means I have to do some changes for R2 as well as R3. Okay, look at this method. Whatever you have here, so I wrote R2, for example, I copy it again. So R2, R2. Okay, R3, R3. Then, so R2, R2. What is the element I want to convert into 0 in R2? It is -1. So whatever the element that I have, I put its opposite sign, which is +1, and multiply it by R1. So I repeat, R2, R2, this element, I write the opposite sign, and I multiply it by the raw R1. Why? Because this is the row that contains the 1 in the corresponding column. Let's do that again for R3. So R3, R3. What is the element I want to convert into 0? It is 3. +3, so I put -3, and again I multiply it by R1. Okay, always works. This always works, provided the leading entry is 1. Now, let's see what this matrix looks like now. So, the first row remains unchanged, 1, 1, 2, 8. Now, R2 plus 1 R1, or simply R2 plus R1. So -1 plus 1, that is 0. And yes, we got 0, and that's what we're looking for. That's what we have to find, right? Or to make it look like 0. -2 plus 1, that's a -1. 3 plus 2, that is 5. 1 plus 8, that is 9. And that's R2. Move on to R3. 3 minus 3 times R1. So I multiply R1 by 3, right? And then subtract it from R3. So 3 minus 3 times 1, that is 0. -7 minus 3 times 1, so -7 minus 3 times 1, that is what? That is a -10. 4 minus 3 times 2 becomes what? It becomes 4 minus 6, that's a -2. And 10 minus 3 times 8, that is 10 minus 24, and it's a -14. And here we have to be very careful while we're doing calculations. As you can see, we have to do all the calculations slowly and carefully in order not to do any mistakes. Okay, what is next? Now we have to convert the leading entry in the second row into 1, and then repeat the same scenario. Convert all the remaining elements in the column into zeros. How do I convert this into 1? Well, it's -1. This means I simply multiply R2 by -1. So I will convert R2 into -R2, and our new matrix becomes what? Becomes 1, 1, 2, and 8, 0, 1, -5, and -9. I'm multiplying everything by -1. And the third row remains as is. All right. I want to convert this and this into zeros, which means I have to apply changes to R1 and R3. So R1, as we said, we copy it, R1, R1. What is the number that I convert into 0? It's 1. So I put -1, but I have to multiply it now by R2. Same for R3, R3, R3. The number when I convert into 0 is -10, so it becomes +10 times R2. And the corresponding matrix becomes, so R1 minus R2, 1 minus 0, that is 1. 1 minus 1, that is 0. 2 minus -5, that is a +7. And 8 minus -9, right? That's a 17. R2 remains as is. And R3, 0, I multiply R2 by 10 and then add it to R3. So 0 plus 10 times 0, that is a 0. Minus 10 plus 10 times 1, so it's a -10 plus 10, that is a 0. Minus 2 plus 10 times -5, so 10 times -5, that's a -50. Minus 2, that's a -52. And minus 14 plus 10 times -9, right? It becomes minus 14 minus 90, and it's a -1. It is a -104. Now you might tell me, well, I can stop here. I can find Z and then move backward. Yeah, but I would like to complete the entire recipe just to show you how to convert this into the RREF completely. Okay? But again, there are always shortcuts. But I would like to do the standard method just in case, so that it works for any matrix. So now, again, what is the next step? I think you might have guessed, right? So this has to be converted into 1, and everything up in the same column into zeros. So I will do the same story. So how do I convert this into 1? I multiply the entire row by 1 over -52. So R3 becomes R3 times 1 over -52, right? And it becomes what? It becomes, of course, 1, 0, 7, 17. That's our first row. The second row is 0, 1, -5, -9, and I have to multiply this by 1 over -52 or divide by -52, so it becomes 0, 0, 1, and 2, and obviously Z here is equal to 2. So I have to convert the -7 and the -5 into zeros. So again, I have to do changes to R2 and R1. So R1, that's a 7. So I have to do -7 times R3 now. R2, I want to convert -5 into 0. So it becomes +5 times R3. And we do the calculations. I'm going to leave the calculations for you. If you have any questions, you can write down in the comments and I will answer. So the final matrix will be 1, 0, 0, 0, 1, 0, 0, 0, 1. And the right column is 3, 1, and 2. And now, keep in mind or remember that this column corresponds to X. And this column corresponds to the coefficients of Y. And this column corresponds to the coefficients of Z. In other words, when I convert it, when I write it back into a linear system, it looks like the following. So 1x plus 0y plus 0z, which is 1x, which is x, equals to 3. We found x. 0x plus 1y plus 0z is equal to 1. We've got y. 0x plus 0y plus 1z is 2. And we've got x, y, and z. So this is how we apply the Gauss-Jordan elimination method. and in order to convert a linear system into a simpler one and solve it. I'm going to do one more example, one more general example. I will write the system and then the corresponding augmented matrix. I'm going to leave the calculations for you as an exercise to convert it, to apply the recipe, the Gauss-Jordan elimination method. Okay, so I'm going to jump right away into the final answer, and I want to show you what happens next. What about this system? So here we have, as you can see, we have 3 equations with 4 unknowns or 4 variables. So the augmented matrix is 1, 1, 2, and minus 1, then 4, and 0, 3, minus 1, and 4, and 2, and 1, 2, minus 3, 5, and 0. So we do all the work, and we end up with this. Now, after we have got the RREF for the coefficient matrix, now we bring it back to its linear system form. Now here x1 is equal to 1, that's good. But x2 plus x4 is equal to 1, and x3 minus x4 equal to 1. Here we cannot find just one solution for x2, x3, and x4, right? Because for these guys here, we have more unknowns or more variables than equations. We have 3 variables with 2 equations. What does this mean? Well, let's, for example, give x4 the value 1. Then I will get x2 is equal to 0 and x3 is equal to 2. Give x4 the value 0. Then x2 is 1 and x3 is 1. So every single time I give x4 a value, I'm going to get another values or new values for x2 and x3. Oh, this means that we are dealing with a system which contains or which has infinitely many solutions, right? We have infinitely many solutions here. So how would I express that? Well, I'm not going to say if I give x4 the value whatever, then etc., right? I'm not going to say it like that. We need to write it mathematically. So we could say that let x4 be equal to t. Then if you give x4 the value t, then you'll be able to find x2 and x3, each one in terms of t. This t is called what? A parameter. Okay, so we end up with an infinite number of solutions, and all of them depend on this parameter t, right, which is equal to x4, and x4 in this case is called a free variable. Free variable because it can take any value, right? Since it can take any value x4, which is equal to t, we call it free variable. So in this case, we've ended up with a system which contains infinitely many solutions. So let's see what the final answer becomes. So x1 actually is only 1, right? x2 becomes what? Becomes 1 minus x4, which is 1 minus t. x3 becomes 1 plus x4, that is 1 plus t. And finally, x4 is simply equal to t. And what is t? T, well, is any value. T belongs to R, is any real number. So this is an example where you end up with an infinite number of solutions. Now here we used one parameter, but in some cases you might use more parameters, and many students here get confused, especially here when we have more than one parameter and we have large systems. I mean, is there any way to be sure that we have used the right number of parameters? I will answer this question by showing you another example, but again, I'm going to jump to the final step and tell you how to deal with these parameters. Let's say we have this system. Now, let's assume that the variables are x1, x2, x3, and x4. And let us write the remaining, or let's convert it back, bring it back to a system, to the linear system form. So x1 minus 2x2 plus 0x3 plus x4 is equal to 2. 0x1, 0x2, x3 minus 2x4 is equal to 1. Now here, well, first of all, the parameter or the variable which shows up in almost all the equations, we give it the first parameter. We give it a value of parameter. So for example, x4 shows up here and here. So let it be equal to t. So if x4 is equal to t here, then we are able to find x3. x3 equals, we'll see. But if x4, even if x4 is equal to t, right, we're still stuck with two variables here, x1 and x2. So I repeat, if I give x4 a parameter, and since it shows up in both equations, that's obvious that x4 will be equal to some t, but this is not going to be sufficient here because we're still stuck with two variables, which means I will need another parameter. Should I give it to x1 or x2? Actually, it doesn't matter. We can say let x2 equal to s, or let x1 equal to s. It doesn't matter, okay? But if I say x2 is equal to s, of course, this s will be different from the s if I use it to x1, okay? But in general, I can let either x1 or x2 equal to s. So let x4 equal to t, and let me give x2 the value s. So this is x4 as well equal to t, which means that I have used two parameters here. Now again, let me answer the question. How would I know, or can I know, is there any way to know beforehand that I will need, for example, two parameters here? The answer is yes. I look at the reduced form of the matrix, of the coefficient matrix. This is RREF. The method also works for if the matrix was in the REF, not necessarily in the RREF. So I repeat, in order to know how many parameters I do need for a system, I need the coefficient matrix to be in the REF, at least. Since this is in the RREF, of course, that's good. In the RREF or the REF, I count the number of the variables, which is 4. Here we have 4 variables. Then I minus 4 variables minus what? Minus the number of the remaining non-zero rows. How many non-zero rows we have here? 1 and 2. This is a 0 row. So I do the number of parameters minus the number of the remaining non-zero rows in the REF, or obviously RREF. And the answer that I get will be what? Will be the number of the parameters I need for this equation, or for this system, sorry. So we get 2. And yes, we got t and s. We did need 2 variables. So that's actually, I think it really helps. So we end up with what? We end up with x4 is equal to t. Then plug it in here. You get x3 is equal to what? It is equal to 1 plus 2x4. That's 1 plus 2t. X2, we gave it the value s. And x1 is what? Is 2x2, which means 2s, minus x4, that is a negative t, plus 2, and of course, t and s belong to R. Okay, so now we know how to solve a linear system using the Gauss elimination or the Gauss-Jordan elimination method. We still have one more thing remaining in this chapter, linear systems, which is homogeneous linear systems. When do we call a system homogeneous, and how to solve this system? It's not very different from that, just one little information or a couple of little information. And after that, we move on to matrix algebra. And that will be in the next video. See you then.